Hello, welcome back to LeetCode Daily Live, where I do the daily question raw and uncut. So we have a medium today. It's called closest prime numbers in range. So given two positive integers, left and right, so we have some range. Find two integers, num1 and num2, right? So I'm guessing we want to find the prime number pair that's the closest to each other. Yeah, so the minimum and return a positive integer array. So return the two numbers. If they're multiple, we want to return the one with the smallest. If no such numbers exist, right, yeah, so we just return like that. What are the bounds though? So it's only up to 1,000,000. So that means it is possible to actually find all the primes, I think. So this reminds me of Siev's algorithm. So what Sieve does is so let's say you have a bunch of numbers, right? Something like this. What Sieve does is that it basically just goes through every it basically just goes through every number, and well, except one, but like it starts at 2, and every multiple of 2 it will just cross it out, and then for the next number it will look whether it is crossed out or not. If it is crossed out, then we don't have to look at that. So now we have 3, so we want to cross out 6, like 3, 6, 9. Remember we are not crossing out the first one because that's just like 1 times 3, right? So it's not like composite, which is the opposite of prime. Next one we look at 4 already crossed out, so we don't have to do anything. And then we have 5 here, so like in 5, like we'll cross out 10. Like if we have more number, we will be crossing out like 15. Like when we have 7, we'll be crossing out 14, which should have been crossed out here already, but like you have like 49 at the back that needs crossing out. And this algorithm is actually ON log n. Where does the log n come from? It actually comes from this sequence. So if the bottom is prime, and then like you're summing up to like the like prime n, apparently it's this. It's like pretty tedious to prove. Well, I'm sure there are lots of proof online, but like basically we can get all the prime numbers in n log n, which we only have 1,000,000, so we can definitely fit that in. And also yeah, and then we just find all the prime and then get all of them out, and then we just check each pair. Okay, easy enough. So I want to run Sieve. So Sieve algorithm. So what we want is I guess we can technically generate 1 to 1,000,000 every time. Is there any nicer way for left right? I guess not, because the other option is like you have like for each number you have to check for each prime, but then that means like you're basically finding all the primes anyways, so it's like kind of redundant, I think. Yeah, so yeah, let's just generate all the numbers, like the easiest way of doing this. So what we want is we want from 1 to 1,000,000. So we can do like is prime false for dash in range. Just do right. Yeah, just do max right or something. 1 million. But then we actually need to add one, because like we can have a million there as well. Yeah, so what we want to do is, so this array goes from 0 all the way to a million, right? Like in terms of the index. So we can just do for I in range. Well, we want to start at 2, and then we want to end at a million, right? So if it's prime I, so if it is still a prime, what we want to do is for I think we want, do we want a starter? We probably don't need that. So we can just do for j in range. Well, what do we want to do? We want to go from I times 2. So like if this is 2, we find that it is prime. We actually want to start at like the next multiple, right? So like 3, we want to start 6. 7, we want to start at 14. So that's where the times 2 comes from. Our end bound is going to be, well, all the way till the end, but we actually want to step by I. So like we want to like 4, 6, 8 all the way up to a million, right? So that's what we are doing here. And then is prime, j would be equal to false, true. That means, yeah, we actually need to, oh wait, we should set this to true actually. Yeah, we should set this to true. And then set this, yeah, and then we can set this to false. That makes more sense. Yeah. So we will be able to get all the primes. I guess we should also just do this just to make sure nothing goes wrong. Yeah, so 0 and 1 are not primes. So the definition of prime is that it only has 2 factors. Well, it only has 1, so it's technically not a prime. Right. So what we can do now is we can have the so prime array, and we basically just go through its prime again. So for I in range, yeah, so again 2 all the way to max right plus 1. Yeah, honestly, we don't even need that, but I just put it in just for safety. So if the number is still prime, well, we can push it into the prime array, right? But we also need one more condition. So and so we want to make sure that I is actually like inclusive in the left to right range. If that's true, we can just append that. So like let's say for 10 to 19, we're gonna get like these here now. I guess we can do a short print. Just make sure we're getting the correct thing, and then we just return something like that. Yeah, let's just check test case 1 whether we are printing the correct things. Yeah, so that looks good. And now what we want to do is, so if the length of prime array, if it is less than 2, so if it is like 0 or 1, we can't actually form a pair. So we just want to return the stub specified here. And then yeah, we can just check for each pair afterwards. So for I in range, so length of prime array minus 1. So what we want is, we want yeah, we want the pair, so smallest pair um should be equal to like something. So um well, we guarantee to like have something there. So we can have a stop for now. So smallest distance. If we set this as well infinity, then it will guarantee to be replaced by anything in here. So we don't actually have to worry about that. So if smallest distance is larger, and we're doing larger because if they're equal, the we want the smallest, right? Yeah, multiple. Yeah, with the smallest number value, and we are like this prime array is sorted like because of the loop, and therefore, like we will look at the smallest ones first. So yeah, so that's why like we are doing strictly greater here. So smallest dist, right. Yeah, we can just do I plus 1 minus I. So if that's the case, we want to set that to this, and then for our smallest pair, I guess we can make an array here, because we're returning an array anyways. Just do equal, well, prime array I plus 1. So we want to return the smaller number first, right? Yeah, that looks correct. And then return smallest pair. So let's see whether that works or not. I think it should. Yes, seems like it. Surely it doesn't time out, because like I'm actually not sure if Python is like a bit slow there. Okay, it didn't time out, but it took very long. I'm kind of interested what other ways other people are doing. So um so left is max 2 and left. Yeah, okay. Right. That makes sense. That's one edge case. So if left and 1 is 0, so left is a. Oh, right. So this is like left is a even number. Is composite. Wait, they have power. This could be like some algo that I actually don't know of. Yeah, other people are using Thief as well. I'm pretty sure like on paper my code shouldn't actually run that long, because it's only 1,000,000. But yeah, well, yeah, I guess this one is just knowing Thief's algorithm. But otherwise, I'll see you guys tomorrow. Bye.